Okay, so today what we're going to be talking about in 6.5 with this worksheet is trying to produce graphs of the square root of a square root function and a cube root function. Okay, these are the two different equations we're working with. Now, a square root and a cube root function, those are the inverses of an x squared and an x cubed equation. So the most basic functions are y equals x squared and y equals x cubed. What we're going to do today is we're going to work with their inverses. So just thinking our way through this, the opposite of an x cubed would be x to the 1/3 or the cube root of x. And so the inverse would be y equals the cube root of x. And that makes sense because if you're going to get rid of a cube, you would cube root. And we'll talk about how to produce that graph here in a second. The other, and this is where it gets a little bit trickier, I'm going to show you that substitution and the simplification for this. If I tried to find the inverse of y equals x squared, we learned last time that you trade x and y places, and then you solve for y. When I solve for y, the only thing to remove is the square. To remove a square, we take the square root. This is where we run into a little bit of a problem. When we take the square root, it does cancel the square. But because we are the ones who inserted the square root into the problem, we're supposed to create a plus or minus in front. Now that might not seem really relevant to start with, but we're going to have a problem because of the plus or minus when we go to graph this. Specifically because we only want to work with functions. And if we go and take a really simple idea, let's grab Desmos here real quick. And if we go to Desmos and look at the graph of these, hopefully we can start to see something that happens. If I were to graph y equals x to the second, okay, there's our x squared equation that we're used to seeing. If I graph y equals, and the calculator, this computer's going to have a hard time doing the plus or minus, so I have to do it in two stages. If I do the positive square root of x, and then if I do y equals the negative square root of x, we get the same parabola. You can see how it's kind of been turned and laid down on its side. The reason I say that we start to have a problem is if we take the vertical line test, which is when we used to do like x equals 3. Okay, if I take this line, x equals 3, do you see how the purple line is going to hit our square root graph more than once? That makes it a non-function, which is a problem. Because when I say x is 3, I only want one answer. I don't want two different answers. And so we have this non-function situation. So when we graph a square root graph, in order to maintain the concept of a function, we're only ever going to be able to graph one side or the other. The equation is either going to be positive or it's going to be negative. And so when we look at that situation, if we dropped one side, if we kept only the positive half of the parabola, okay, or the square root graph, then we get the upper half. If we only keep the lower half of the negative, then we get the lower half. And so when we graph a square root graph, we're not going to try and graph the whole thing. We're only ever going to graph either the positive or the negative. And that'll be indicated by the problems that we look at. Now, some things that are really interesting about this graph, if we start to look at its behavior, okay, we might want to talk about its domain and its range, meaning the values of x that we're allowed to use and the values of y that we're allowed to use. If you look at this graph in blue, let's get rid of everybody else. If we just look at this graph in blue, it goes off to the right forever. And that's true. It's going to drift to the right, and it's sliding up as it goes to the right. However, back here, we get to 0, 0, and the graph doesn't exist on the left of 0 or below 0. That's because if we take the square root of a negative, we get an imaginary number. And so we can't live in the negative region. But if we make small adjustments to the equation, like let's say I put a -3, notice the graph shifts to the right. If I make that -3 a +3, it shifts to the left. And so we start to see these changes and these adjustments. The good news is we've already learned how to use these adjustments in previous stuff. when we did quadratics before. So let's take a look at producing some of these graphs by hand from our worksheet. So if you guys will, let's just take a look at question number 1 as a really simple example that we can work off of. Let's get a little bit bigger here. There we go. Question number 1. We have the equation y equals negative square root of x plus 2 plus 1. Notice the plus 1 is outside of the root, but the plus 2 is inside of the root. That's great for us to be able to distinguish in and out. Now, as we start into this, I'm going to tell you, you can absolutely use your graphing calculator, and you probably should. But I want to teach you how to identify the critical value that we really need to know when we start these graphs. If you guys remember back when we were talking about quadratics in vertex form, we always said that if you had x minus 2 squared plus 5, that the vertex was at the opposite of the thing with x, and whatever number was added or subtracted at the end. I could find the vertex of y equals negative x minus 2 squared plus 5 at 2, 5 in a pretty simple way. The same rules apply to square root graphs. So what is it's not really the vertex, it's actually what we're going to call the starting point, but we can treat it like the vertex in terms of the way we look for it. What would the vertex be for question number 1? What would it be for the x? Negative 2, positive 1. Absolutely. Negative 2, 1. So I can actually go to my graph to negative 2 and 1, put a dot. I know that that is going to be the starting point of my graph. And it's either going to go up to the right or down to the right. One way or another, it's drifting to the right. For me to figure out what it looks like, I'm probably still going to use my calculator to help me with this. So let's grab our calculator and see how the TI-84 is going to handle this. We'll go to our y equals. When you have a negative in front of your square root, you really do need to make sure you push the negative symbol, not minus. So I'll push negative, get my square root symbol in here, x, whoops, I gotta go back, x plus 2. How do I get out of the square root? Just push to the right. It'll pop us out of the root, and then I can write plus 1. If I graph it, does it look like it might be starting over there at negative 2, 1? You can kind of see where the graph kind of begins. And I need to know more data. So I need more points to plot. Let's look at the table and see what weird things are happening. If I go to the table and I go back past negative 2, 1 to negative numbers like negative 6 and negative 5, what pops up on my screen for my y value? Errors. Why am I getting errors there? Because they're imaginary numbers. If you put negative 6 into that equation for x, negative 6 plus 2 is negative 4. The square root of negative 4 is 2i. I have an imaginary number, so I can't plot that on a traditional graph. So I'm going to skip those values. What's the first value that doesn't have an error? Negative 2, 1, just where we said it would be. So if you aren't sure how to decipher that from the equation, you can always go look for the first non-error in the problem set. Okay, and then we keep going. I need to plot some more points. So where else should I plot a point? Negative 1, 0. So put a dot at negative 1, 0. Those of you who still have your calculator open, what's another point further down the line? 2, negative 1. So I'll plot 2, negative 1. How many points do you think it takes to create the curve that I'm looking for? If we remember the process of drawing a quadratic, the U shapes, I always said 5. The vertex and 2 on each side. Well, we have the vertex, that's the first point, and we have 2 to the side that it exists on. We aren't graphing the other side, so 3 points is going to be enough for a square root graph. And now I'm going to go ahead and create my sketch. Now, as I do this, keep in mind, the graph starts at negative 2, 1. So I'm going to start right here at negative 2, 1, and I'm going to draw that half parabola drifting off to the right. I really should drop a little bit more. Let's go like that. Something like that. Okay. Go back and clean that up. Okay, so maybe, again, this is hard to draw with this board, but it should look I keep sliding up. Okay, should look something like that. Your square root graphs are never going to be perfect, but should look something like that. There is one more step for all of these graphs. We need to state the domain and the range. The domain is all of the x's that are valid values to plug into the equation. And the range are all of the possible y values we get back. So when I do the domain, I'll do a D for domain and R for range. The domain is always about the x, and the range is always about y. X, then y. Domain, range, x, y. So the question is, what x's am I allowed to use without having a problem when I go to evaluate? Can I use 0? Could I plug 0 into this equation and get an answer? I can. It might be a decimal, and if I look at my table, sure enough, 0 is negative 0.4142. Could I plug in negative 1? Yeah, it gives me 0. Could I plug in 7? Sure, it's going to give me a number. What's a number I can't plug in? Negative 3, or negative 4, or negative 5. I don't want to plug in numbers that don't create a curve, don't create the graph. So I want to say that my domain, the x, is greater than or equal to my first x value. The first x value was negative 2. That's what this number, why it's so important to go and find that first value. Okay, for those of you who don't know how to tell which way greater than points and which way less than points, it's really simple. Which way did we point our arrow? To the right. We use the exact same symbol with an equal to bar underneath it. Those of you who didn't know, the greater than less than symbols were originally created as arrows. It literally reads x is to the right of negative 2. That's what that symbol represents. So we use the word greater than, it kind of confuses people, but that is the greater than equal to symbol. And all of these graphs are going to point to the right. So the domain will always be greater than equal to. That won't change. What will change is the y values. If you look at the y values on the table that are valid y values, are they getting bigger or smaller than that first one? They're turning negative, aren't they? Which means they're getting smaller, more negative. So we need something that tells us that we are going down in value, which should be the less than or equal to symbol. And what's our first value? 1. So our domain and range for all our square root graphs are going to be written as x is greater than equal to some value and y is either greater than or less than some value. Does anybody have a guess why this turned out to be a less than symbol, whereas other ones will be greater than symbols? Something about the equation. Clara? It goes down, but why does it go down? That's right. Because the equation starts with the negative symbol, it's the bottom half, so it's the downward half. If it had been a positive, it would have gone up, and it would have had a range that's greater than equal to instead of less than equal to. Okay? All of your square root graphs are going to graph the same way. On a question like number 2, where it doesn't have anything added or subtracted, what do you think that means? So it's going to be the positive half. Where's the vertex going to be? It'll be at 0, 0, because there's nothing added or subtracted. So that makes it easy to find the vertex. Now, one thing that's going to throw you off once in a while, sorry, kids are going to start showing up. One thing that's going to throw you off once in a while is when you look at equations like number 3. Number 3 is not harder than any others. It's just written differently. Do you see the minus 1 plus the square root? That minus 1 is the same as putting a minus 1 at the back end. Like I could push the minus 1 to the tail end, or I can leave it in the front. If you're just putting it in the calculator, it doesn't really matter what format it's in. It only matters if you're trying to decipher the vertex by hand. If you want to find the vertex by hand, that minus 1 should be at the end of the equation instead of at the front. On a question like number 4, this negative 2 is not added or subtracted, so this is like a multiplier. It has nothing to do with the vertex. The 3 at the end has something to do with the vertex. Okay, So that's how those work. Let's look at a cube root graph. These cube root graphs are snuck in here throughout the process or throughout the problem set. Let's see if I can find a... Yeah, we'll do number 15. Cube root graphs, remember a cube root of a negative number, when we did the cube root of a number like -8, I think we did -125 on a worksheet a ways back. Instead of getting imaginary numbers, we actually got results to these. Because what number times itself 3 times produces -8? It's actually exactly -2. And so because that's true, we won't have these restrictions on our domain and range like we did with the other. There aren't going to be imaginary numbers that we can't graph. So let's take a look at this. I'm going to tweak one thing as we get started. This -2 at the beginning is added to the root, so I'm just going to push it to the back. Now, this is probably more important to find the vertex for these cube root graphs than it is for the square roots. The square roots are easy to find in the graph or in the table. The vertex here, I think we really need to know how to find it by hand. So what's with the x? It's +4. So I'm going to use -4 because it was grouped with an x. And then outside on the tail end is -2. So that's my vertex, or my center point. This is not going to have a vertex so much. It'll be what's called a center. So I'm going to go to -4, -2, and I'm going to draw a dot. The rest of this is all going to come out of my calculator. When I was in high school, we learned how to do this by hand. And I'm just going to tell you, we have technology that's way beyond what we were using. I even had access to a calculator at the time, graphing calc, and still didn't know how to use the thing. So we're just going to learn how to use our calculator. Now there are some catches to this. We're going to type in our 2. All right. How do I get the cube root function in my calculator? You can go to Math and option 4, I think it is, or you could do parentheses. We could write this as 2 parentheses x plus 4 to the 1/3 power minus 2. A 1/3 exponent is the same as a cube root. So you could do it that way if you don't want to be digging around for a cube root. But if you don't mind digging for a cube root, it's in the math option, option number 4. And you can see that produces that cubed root, x plus 4, get out of your cube root, minus 2. And if I graph that, I don't get a square root graph. I get sort of an S shape. Okay? It's sort of a zigzag. And what we're looking at is the opposite. We're looking at the inverse of something that looks kind of like this. So there's a traditional x cubed equation, and we're looking at its inverse, its rotated and reflected version. So do you see where there's kind of this is an error in the calculator's pixelations, but can you see in your calculator how there's a little hole in the graph, a little tiny dot that seems to be missing? That's basically where your vertex is. And it just has to do with the pixelation around it. But does that look like it's at about -4, -2? Kind of in that area? That's good. When I go to my table to plot points, I want that to kind of be in the middle of my page. So I'm going to scroll till -4, -2 is kind of in the middle. So mine looks like it's going from -7 to -1. The reason I like that is I want to gather points on both sides of my center. So what's a point I can plot that's close to -4, -2? So -3, would be like right there. And -5, -4? All right. I've got 3 dots right there. Is that enough to create the curve? No, and the reason why? You ask anybody to connect those dots, they're going to draw a straight line. They're not going to create a curve. So we're going to have to go out further to create another point. Now what I'm going to ask you to do, I'm going to give you choice here. You don't have to go out to the next whole number, because those are about 7 more units out. And sometimes that's really far. But I am going to ask you to go out at least 3 units further away from that center. So For instance, going to -1 and -7 will work. If I were to go to -7, it's -4.9. -7, -4.9 would be like right around there. You could also go to the positives. If you just keep going, what do we get to? 4,2. You could go all the way out and do 4,2. You can choose balanced points or you can choose unbalanced points. You just need to have a total of 5 points. The center point and 2 on each side. Okay? When we go to create this curve, most students have a hard time creating the S shape as a nice fluid curve. What I found has worked for most kids is to start in the vertex, draw the curve to the right, go back to the vertex, draw the curve to the left. So it should look something like this, and pardon my, it's going to look a little funny, but we'll do the best we can. So there's the curve to the right, and then I'm going to pull down and do the curve to the left. Sorry, like I said, I get a little funky sometimes on that. So now we want to talk about the last piece, which is its domain and its range. This graph doesn't have an error in it. If you look at it, how far to the right does this graph go? It goes forever. How far to the left does it go? Forever. And there are no stops or starts, right? So it's a fluid curve from left to right. So we would say that the domain is all real numbers. And so right here, I'm going to put domain is all real numbers. You pick any real number, plug it in the calculator, it's going to give us an answer. It can solve all of them. Well, the range, remember, is the y values. How far up is this thing going to go? We know it goes to at least 2, but it's going to continue to drift its way upward forever. And how far down is it going to go? It's going to drift down forever. And so this is an example of a problem that has a domain and a range of all real numbers. Now, mathematicians are by nature lazy, correct? That's all human beings are. So rather than writing out the words all real numbers over and over and over again, which you will do, mathematicians have a symbolic representation of all real numbers. If you've ever seen like the paragraph symbol that you use in like an English class, you guys know what I mean? The double line backwards P. We don't do it backwards, but it is a double line. So if you do want to say all real numbers, you do a double line and make it a capital R. That symbol is the symbolic representation of all real numbers. So rather than having to write out the words all real numbers, you can use that symbol anytime you'd like to. Or you can write out all real numbers. Now, every one of these graphs that you do today on your worksheet is a rewrite of the same problem. It shifts around, slides left and right, up and down, and stretches a little. But the general rules don't change, which means the domain and range rules will always be the same structure for square roots and always be the same structure for cube roots. So this domain and range is the domain and range of all cube root graphs, meaning I can jump around, find all the cube root graphs, and claim the domain and range without ever graphing them. Now, you still need to graph them for the sake of the homework, but hopefully that's enough to kind of get you going on the homework and some good examples, and see you guys in class.